Hi again everyone. Welcome to the next lesson for machine learning. Today we're going to talk about neural networks, which you may also know by the term deep learning. While there are some minor differences between the two, essentially they are the same. So let's just dive right in. So today's goal is to help everyone understand that neural networks attempt to model the network of neurons in the human brain, and hence the term neural networks. One of the essential questions we're going to explore today is how do neural networks take inspiration from human neurobiology? And I think this is important because we are studying artificial intelligence here. Artificial intelligence gets that term because we are trying to understand the human brain, human intelligence, and trying to replicate that in a machine. So it behooves us to explore the human brain, which is the source of our intelligence, right? In order to try to mimic that in a machine to create artificial intelligence. We'll also talk about how neural networks learn automatically through repeated exposure to the same training examples. And that's interesting because realistically, when humans learn, we don't always see new examples all the time. Sometimes we see the same cat or the same dog, and then through the repeated exposure, we are able to strengthen that connection with the image and the name of the object. I think realistically as well, we do not have infinitely big training data sets, right? So if our neural network is able to learn to get better by looking at the same training examples, that would be even better. We can make the most out of our small data sets. So let's take a look at where neural networks falls in this whole scheme or this whole machine learning paradigm. We've talked about supervised learning, unsupervised learning. The nice thing is that neural networks can be used for both supervised and unsupervised. Neural networks can be used to do classification and regression tasks, and even in some of the tasks that we do in unsupervised learning. For example, you can use neural networks to create autoencoders. Autoencoders are really awesome because we're trying to create a network that can recreate the training examples itself, but perhaps using less data points. So for example, you have let's say you have images. Instead of am I able to reliably recreate those images using maybe fewer pixels, or maybe an image of less, or storing just a few of the pixels in the image. Yeah, so those are what autoencoders are. We are trying to, in a sense, recreate the data itself automatically. Yeah, and neural networks can be used for that task. So you can see the neural networks are very, very versatile. They can be used for a lot of tasks, and that's also one of the reasons why neural networks or deep learning is very, very popular. It also performs fairly well for most kind of tasks. In the past, when we talk about supervised learning, we have mentioned that certain algorithms are good at certain tasks, but not so good at certain other tasks. Neural networks can be used for pretty much everything and does reasonably well for everything. So that's why neural networks or deep learning is so popular in this day and age. Okay. So we did want to talk about neurobiology and how neural networks takes inspiration from this. So this, what you're seeing right now, is a biological neuron. Okay, these are your brain cells. So the left is an image, diagrammatic drawing of your brain cell. Your brain cell takes in inputs from the dendrites. These inputs can either be from your 5 senses, your eyes, your skin, your nose, for example, or it could be from another neuron, another brain cell. So it takes in the inputs, it processes the inputs in the nucleus area, and if, let's say, they decide, the brain cell has processed the information and decides that it is worth taking action on. So let's say something has happened and you want to take an action. The information is sent through the axon to the next brain cell or the next perhaps muscle in order to take action, to tell it to take action, take a certain action. So maybe it will pass the information on to the next brain cell, which will alert maybe your muscles to move in a certain way, or maybe it will just pass the information to the next brain cell for it to process further and see whether further action is needed. So that is how your brain cell works. Okay, you hear me use the terms input and output. That really sounds like a computer program, right? So it takes in input from the dendrites and output through the axons to the synapses. Okay, on the right you see how the brain cells are interconnected. The pink dots you see are the nucleuses, the cell bodies of your brain cell, and you can see that the dendrites and the axons are reaching out kind of like a spider web to interconnect with other brain cells. So this is roughly how it looks like in your brain. Okay, how does your brain work? Okay. So moving on from a brain cell, this is what we want to replicate in an artificial neuron. Okay, that an artificial neuron is what we call a perceptron. Okay, you can see how the term perceptron has taken inspiration from the word neuron. So a perceptron is a neural network unit, okay, artificial neural network unit, or you can call it an artificial neuron, that does certain computations on the input data to make certain decisions. So you can see at the bottom here is a simplified diagram of your neuron. You have your inputs coming in and then your outputs going out. Okay, just like the dendrites taking inputs, they process in the cell body and then goes out through the axons. Okay, so if you were to replicate this as a piece of code, it's basically taking in inputs, doing some mathematical function, okay, because code is always math, right? So we do some mathematical function on it, and then we decide whether we want to what value to output to pass to the next neuron, or to output to make a decision. Okay, and if we have many perceptrons, we are able to build a neural network. So you notice how all the perceptrons, each circle here is a perceptron, right? So in the input layer, it takes in the input from the external world, okay, or the data that you feed it, and then it will feed that data into the next layer. And you notice each perceptron in the input layer is connected to the next layer. Okay, all these green perceptrons here. Okay, and these green perceptrons take in the inputs from all the input layer perceptrons, and it outputs to all the perceptrons in the next layer. Okay, and so forth until I get to the output layer. The output layer takes input from all the last hidden layer perceptrons, and it outputs a certain value. Right. So this interconnectedness is also what you see in the brain. As the diagram of the brain is of course less neat, right? So but basically that is what you see. Neurons are interconnected with each other, just like what you see here. Okay, in the hidden layers especially. So the hidden layers are called hidden layers because they are the layers that do all the legwork, all the groundwork. They don't interact with the outside world, unlike the input layer that takes the inputs from the outside world, and the output layer which outputs the decision to the user, to the outside world. Right, the hidden layers are the ones inside on the inside doing all the heavy work. Okay. Sometimes in a neural network you may have more than one output. So for example, like this, the last hidden layer is outputting or feeding their decisions or their values into each of the output, the perceptrons in the output layer, and then each perceptron in the output layer will output one value. This is usually true, or this is usually what you see if you have a decision to make that has more than one outcome, okay, as opposed to just a true and false outcome. So neural networks have also been used quite famously to detect or to identify handwritten digits. So for that case, I will have 10 perceptrons in the output layer, one for each digit. So one perceptron will be in charge of deciding whether this is a digit 0 or not. Next perceptron will be in charge of deciding whether this is digit 1 or not. So I have 10 of them from 0 to 9, and then I will see which perceptron has the highest output value. I will say that that's the highest probability for being that digit, and I'll classify the input as being that digit. Okay, so let's look a bit closer at the so-called anatomy of a perceptron. Okay, you can see how this is very similar to what we saw in the neuron. Okay, you have your cell body, okay, right in the middle. It takes in the inputs, and then there is a output as well. So the inputs are usually denoted by x's, x1, x2, all the way to xm, depending on how many inputs I have. They are combined with a weighted sum, which means that each input has given a weight w1 to wm, and then at the middle I also add a bias value, a b, and that is the value for that the cell body gives me, right? And then to decide what value to pass on to the next perceptron, I will have to pass it through an activation function. So this is the math behind the perceptron. I take in the inputs x values, I multiply it by the w's, and I add them together with a bias, and then I pass it through another function called activation function to decide whether what value I want to pass to the next layer, or maybe to output as a prediction. Okay. So the weighted sum is something that we've seen quite before actually. It is quite similar to the linear combination that we see in our best fit line, our linear regression line. Yeah. So what the weights mean is that if the input is very important in determining the output of this perceptron, it should have a higher value. Okay. And then the bias can also change that so-called baseline value. So if all the inputs are 0, the output value, the z value here, will be just the bias. So the bias kind of determines maybe how important this perceptron is in making the final decision. Okay, so the weights and the bias are values that the model will learn. They are initialized at random, and then the model will adjust them automatically as it learns. Yeah. Okay. I do not know whether you can see any similarity with this to your y equals mx plus c, right? So you have your x value multiplied by a gradient value m, and then you add a value behind it, right? Your constant value. So it is similar, just that I have multiple m's now. Okay. Sometimes, and this is where matrices come in very, very handy in computer science. So sometimes when you have a lot of inputs, a lot of weights, it is very tedious to write them all out in an equation like this. So I represent them as a vector. Then I can call my W my weight vector, my W1 all the way to Wn. That forms a weight vector. Okay, so this one is just for your information. If you ever wondered why matrices are so important and why we need to learn that in math, this is one of the reasons. Okay, it's very important. You do see it more and more as you go into higher level computer science as well as physics. Okay. There's also an activation function in your perceptron. So the activation function determines if the neuron will fire or not, or at what value. Okay, because the issue with these perceptrons is that the value z that we see here can go as high as it wants, right? I can set my bias at 1 million, and then the value of z will be 1 million, which may be unfair because some other perceptrons only have a very small bias value. So it's usually important to normalize that value. Okay, set the maximum at 1 and the minimum at either 0 or -1, and then the value of that perceptron, the output value of that perceptron will take on any value between 0 and 1 or -1 and 1. So it doesn't kind of inflate that value of that perceptron. Yeah. So some considerations that we have when choosing the activation function. Okay, we want the computer to be able to calculate this activation function quickly, so that the value can be found quickly, right? Another consideration we have is to make sure that the function is differentiable. What we mean by differentiable is that it can be differentiated, so you can perform some calculus on it. And this is a criterion to help the network learn quickly, because later on we'll need to do some differentiation in order to adjust the weights. Okay. So this is a very basic activation function that usually we do not use because it doesn't normalize the output, right? So it's a linear function. Whatever is input will be the same as the output, right? So yeah, okay, if I input -6 into the activation function, it also outputs -6. If I input 0, it will also output 0, so it doesn't change the value at all. Okay, and it definitely doesn't do that normalization that we talked about. So another function that we can use is the binary step function. So we just set a certain threshold. Any value that's below the threshold, we say that it doesn't fire, the value is 0. Anything that's above the threshold, we say that the perceptron fires. We output a value of 1. Okay. Do know that this function is actually not differentiable, because there is it's very hard to determine what's the value at that threshold. Okay. Should it be 0.5 right in the middle, or should it fire? Does it not fire? So this is another function that is quite often used. Okay, it goes from 0 to 1, and it kind of squashes that input value, okay, between 0 and 1. Okay, so this is what we call a sigmoid function. If you recognize the equation, congratulations, that means you are very familiar with your logistic regression, because we also use that same S-shaped curve function for logistic regression. So this activation function takes in inputs, x inputs on x-axis from -infinity to infinity, and it squashes that output between 0 and 1. So there is that normalization effect on it. Another equation that is very, very famous is called the ReLU function. The ReLU function just takes the max between 0 and x. So if your input to the activation function is negative, the function just outputs a 0. And if the input into the activation function is positive, it will just return the same value. So that's what we mean by maximum of 0 and x. So if it's negative, 0 is higher than the negative value, so I'll output 0. If it is a positive value, that positive value is going to be higher than 0. So the max will be that value x itself. So see, these are some of the more common activation functions being used. So this is how, so now that we've kind of seen all the ingredients of your neural network, let's see how it works in action. Okay, so we have the forward propagation stage. So what happens when we first start the training process is that inputs get thrown into the network through the input layer. Okay, or first your weights get automatically or randomly assigned to a value, and then inputs go in. The output value of each perceptron is calculated by multiplying with the weights, adding the bias, and then that's output, and then passing through the activation function. It goes to the next layer where they also multiply the weights, add the bias, and output, go through the activation function and output, so on and so forth until we get to the end. So the direction of movement of data here is from the left side, the input layer, to the right side, okay, where you get an output value. Okay, so this is what we call forward propagation. Okay. So here you have a few terminology. Okay, the input layer it usually depends on the number of features that you have in your data. Your hidden layers is really something that you can choose. You can have no hidden layers, you can have 5, you can have 10, it's up to you. It's a hyperparameter that you choose. In fact, the number of neurons in each hidden layer is also up to you. You don't have to have the same number as the number of inputs you have. You can have 100,000. Depends on you. Depends on the processing power of your device as well, right? Okay. So each neuron will take in inputs from all neurons. This is a fully connected neural network. Of course, there are some others that do not have full connection. So only some neurons are connected to some certain neurons in the next layer. Okay, but the most basic is when you have all neurons being connected. All neurons from the previous layer outputs to the all neurons in the next layer. Okay, and the more layers you have, the deeper the learning. That's what we call it, and that's how the term deep learning comes in. Okay, the more layers you have, the deeper the processing goes, and the deeper, so-called deeper the learning. Okay, but you may also want to take note that more layers may not be better. Sometimes a simple network with just 2 layers performs better than one with 100 layers, because you're overcomplicating the whole process already. Okay, so your output layer usually represents how many possible outcomes or classes you have in your classification problem. So like I mentioned, in a digit classification problem or digit recognition problem, I have 10 digits in total, so I have 10 perceptrons in my output layer. Okay. The output layer usually uses another activation function called the softmax. Softmax is a bit like your sigmoid. It kind of squashes your outputs into a 0 to 1 value, and that's great because usually you're talking about the likelihood. So each perceptron represents the likelihood that the training example belongs to a certain output class. Okay. So once you've done the forward propagation, now we want to go backwards. So what happens is the output value that I have from my first iteration, my first pass through the network. Okay, I'll compare that. If let's say, especially if it's supervised learning task, right? I'll have answers that I can compare the output value to. So I'll compare the output value with the answers, and then I'll calculate some kind of error, or what we call a loss function. And the goal here, of course, is to reduce the loss, because we want to be as accurate as possible in our predictions. So we'll use that loss function to readjust the weights and the biases in the network. So in order to try to minimize that. Okay, so that process of how the loss function it can be used to minimize the that loss, right? How the network can minimize that loss is through a process, or we will do some differentiation on all the activation functions and all the equations to get the weighted sums equations. Yeah, so that's where the differentiation comes in. So if you want to go watch what goes on in one iteration of forward and backward propagation, you can click on the link here to take a look at what happens at each layer or each stage. Okay, this website is pretty cool because it also shows you some of the math, but do be warned that it's quite advanced beyond what we learn even in secondary school here. Okay, so you notice that this updating of the weights takes place quite often. Okay, and usually this whole process that I just described is just for one training example, one data point in your training data set, right? Because the inputs have to be input one by one into the system, so that and then you get a certain output value, right? So because of that constant updating, it can be a little taxing on your system, a bit tedious, a bit slow. So one way that we try to manage that tediousness is to update the weights only every few inputs. So that's what we call a batch size. So instead of updating with every data point, we update through after a few data points. So that few data points is called every batch. Okay, and the batch size is a hyperparameter that we can manually adjust. So let's say if I have 1,000 training examples and my batch size is 1,000, then my weights are only adjusted once every 1,000 training examples, entire training examples have been passed through the system. Okay, and of course the loss function will kind of aggregate average of all the errors for every training example. Okay, if I want to do an update more frequent, I can change the batch size to 500. So that means after 500 training examples have been seen by the network, I update the weights and then I pass through the next 500. Okay. If I want it more frequent, I can also even do a batch size of 100. So the weights are updated after every 100 training examples. Okay. There's another hyperparameter term called the epoch. The epoch refers to one round after all the training data points have been passed through the network. So when I have a batch size of 1,000, I will only update the weights after 1,000 training examples have gone in. There is one iteration per epoch. Okay, one iteration means one round of updating of weights, forward propagation, and then updating of weights in the back propagation. Right, training. If I have a batch size of 500, I will pass all my data through, pass 500 data points through, update once, that is one iteration, pass the next 500 through, update my weights another time, that is the second iteration. So iterations per epoch, 2. Okay, because the epoch is when all my data points have passed through. Okay, over here, when my batch size is 100, I will pass 100 data points through, update weights once, that's one iteration. Pass the next 100 through, update my weights again, that's the second iteration. And I'll do that 10 times before all my data points have been seen by the network. Right, so that is just one epoch. So 10 iterations, 10 update of weights in one epoch. Okay, so number of epochs here refers to how many times I want to pass my entire data set through the network. So you recall one of the essential questions that we wanted to talk about is how the network improves through repeated exposure to the same training examples. So the more epochs I have, the more more times my network sees the same training examples. But even though it's seen the same training examples before, it actually can improve its performance. Okay, just like for us as humans also, right? We do one question once, we may not get 100% accuracy, we may make certain mistakes. So sometimes we can practice the same question again, and by right, we should improve our accuracy. And every time we try the same question, we should be getting better and better until we should, by right, be perfect at it. Okay, so that number of forward-backward propagation iterations that make up one epoch can be calculated using number of training data points divided by batch size. So iterations per epoch is just number of training data points divided by batch size. So if I have 1,000 training data points and my batch size is 1,000, I only have one iteration per epoch. If I have 1,000 data points and batch size is 100, 1,000 divided by 100 is 10. So 10 iterations per epoch. Okay. There's another hyperparameter called the learning rate. So you may think that learning rate, because the learning rate controls how fast my neural network learns, right? So I don't have all the time in the world. I might want to increase my learning rates. Okay, but it may be intuitive to you to just increase learning rate in order to get your neural network to be ready faster, right? To be perfect faster. But just a word of warning, if you have set too high, your neural network may not even derive at the optimal answer. Okay, because if the learning rate is too high, the updates may be too drastic. It may not be able to arrive at the correct answer, which is at the minimum of this curve. So if you set a smaller learning rate, it will move slowly towards the minimum of the curve, and you get the optimal answer eventually, of course, but you do waste a lot of time getting there. So that's why the learning rate is important. It's kind of a Goldilocks problem, where too low, it takes too long, it's not perfect. Too high, it may not arrive at the correct answer, and it's not perfect either. You just need to get the just right value where you can arrive at the optimal value, the minimum point, swiftly and accurately. So learning rate is another hyperparameter that we sometimes adjust in order to make sure our neural network can learn fast and efficiently. Okay, so this is an exercise that I want you to try later. I will want you to tune the hyperparameters in this simulation here in order to get your neural network to learn. So if you notice this diagram of the data points, okay, we have two classes here, the orange and the blue, and you notice that they are not linearly separable. Okay, if you remember the term linearly separable from when we talked about supervised learning algorithms, linearly separable means that I can draw one line to separate blue on one side, orange on the other side. Okay, but you notice my orange is clustered on the top left, bottom right. My blue is top right, bottom left. Okay, I cannot draw one straight line to cut them into two halves. Okay, with blue on one side and orange on the other side. So this kind of data is usually not very good for support vector machines, for example. Remember when we talked about support vector machines, we wanted data to be linearly separable, right? And even for your logistic regression, it works best when you have linearly separable data. Here, it is not linearly separable. So, what can we do? How well does our neural network work on this data? Okay, it turns out pretty well. Okay, provided you adjust the hyperparameters correctly. We call this the ZOR dataset because this kind of models the output in the ZOR logic gate. Yeah. So when you do this exercise, you don't have to touch the things in the red box. Just leave it. The green boxes are where your hyperparameters are: your learning rate, your activation function, number of hidden layers, number of neurons per layer. These are the things that I want you to play around with in order to get the training loss or the test loss to decrease. So the lower the value, the closer to zero, the better. So the goal that I have set for you is to get the test loss less than or equal to 0.177. Okay. Just to let you know, the initial is kind of set to 0.5. 0.5 means that your accuracy rate is 1 in 2. So you're not any more accurate than a coin toss, okay, to decide whether a new data point is orange or blue. Okay. So this is something that you can try later on. There's also a bonus here. So just now we had a ZOR dataset. I would also want you to try the spiral dataset if you're interested and if you have the time. So you notice the spiral dataset here, the points are kind of like in a circular motion and they kind of spiral around each other, right? So the orange one is on the outside and then the blue is on the inside of the orange, but all in a circular manner. So how well is my machine, is my neural network able to separate this data? Okay, once again, your test loss starts at 0.5, and that means it's no better than a random choice of between orange and blue. Let's see whether we can reduce this further. Okay. So we have almost come to the end of this lesson, but I just want to give a word of warning before we end. Okay, in all things, whenever we do machine learning, we have to remember that machine learning isn't a silver bullet to magically create predictions. Okay? In particular, your neural networks, your deep learning, is not a silver bullet in algorithm that can be used for any data set to magically solve all my problems and predict all my values. Right? It's still important to have a very good data set. So what you see on the right is it's actually a published piece of work in researchers have actually published this in research journals, science journals. So here the task is to predict from a X-ray scan of the lungs to see whether this patient has COVID or not. So your training data is the one on the left, the leftmost one. So this one, the 3 models that are tested have a very high confidence rate that this is a pair of lungs of a COVID patient. So at 99 or 95% confidence that this person has COVID, right? Because there's training data, of course you do better on training data, right? Because that's what you have seen before. In fact, with a neural network, this is what you've seen many, many times before. Okay. With unseen data, which is your test data set, okay, most of the algorithms still perform pretty well. Okay. DNN, NN usually stands for neural network, so these are different types of neural networks. So DNN makes a wrong prediction that this person has no COVID, whereas the other two have a green, have their scores in green. That means they predicted correctly this person has COVID. Okay, and then of course you have the last picture, which is unrelated data. So and the strange thing is that all 3 of your models have predicted that this cat is a pair of lungs with COVID, okay, with 100% confidence even for some of them. Okay, of course, the whole point of this paper is that this set of researchers, they were trying to promote their own neural network. That's why they say ours. Okay, even on very unrelated data, it is able to it has a confidence rate of 50%, which is probably better than everything else, right? Because this is a cat. I'm not supposed to be able to say that this is a pair of lungs with COVID. Yeah, okay, but I mean the ultimate story here is also that with a bad data set, okay, you're not going to get very good results as well. Okay, so if we test it on unrelated data, will it be able to predict for me that this is not a pair of lungs of a COVID patient, right? Okay, so here are some additional readings that you may want to take a look if you're interested in deep learning or neural networks. I personally do like the last 2. Okay, this video is quite informative to explain a bit more of the details of neural networks. I do like these visualizations as well. You can see how it's very cool to see what each layer in your hidden layers especially are doing. So what do the weights look like when visualized? What happens as your neural network trains to a higher level? Yeah, so these 2 are really cool resources that are out there to help us understand what neural networks are. Okay, I say this, but generally, I also have to end off by saying this. Okay, generally, the consensus about neural networks is that while it is like a magic silver bullet, it can solve a lot of problems. It can do classification, regression with surprisingly high accuracy. Neural networks is a bit different from all the other algorithms we've seen so far, because if you notice, all the other algorithms we talk about, there is some kind of logical reasoning behind it. Okay, decision trees, for example, is how we humans make decisions, right? A bunch of if-else statements. If this is the situation, then I will do this, else I will do something else. Yeah. If we talk about k nearest neighbors, we are trying to classify things by association. So if I have this new object and I say that, hey, this new object looks a lot like these other objects we've seen before. Okay, this new object looks a lot like cats, then I will classify it as a cat. Whereas if I have a new object and say, hey, it looks a lot like the dogs, I will call it a dog, right? So all these kind of have logical explanations behind it, right? But neural networks, on the other hand, while we say that it's based off neurobiology, how our brain works, the weights in a neural network seldom have concrete meaning. So earlier I mentioned that the more important the input is, the higher the weight is. That usually is only true for the first hidden layer. The weights of the second hidden layer, the third hidden layer, and so on, it kind of loses that meaning because it doesn't take its input value directly from the data set, right? So how do I predict those weights? Usually, and most of the time we say that there is no real answer to that. So neural networks often comes off as magic. It comes off as there's no logic, there's no the answer or the weights, the parameter values do not give you any indication of anything. So there is some kind of mysteriousness that surrounds the whole idea of neural networks. So whether you as a neural network engineer or as a machine learning engineer is comfortable with that, that really depends on you, how comfortable you are to have this thing that works like magic and no one knows why. Or will you prefer to use a network where the weights mean something, you are able to roughly understand how the computer has made a prediction. Yeah, so that is really up to you as a machine learning expert. Yeah. So that's all that I want to talk about for neural networks. Of course, there's a lot more to talk about, in particular, how you implement them in Python, right? But we'll leave that for another day. We'll leave that for self-exploration even. So until next time, I'll see you again. Bye-bye.